Hi everyone, I'm Chris and welcome back to the lecture on support vector machines of this machine learning course. In this section we derive the dual formulation for support vector machine training. So far, we considered the support vector machine to classify two classes with respect to a separating boundary. This boundary is specified by the parameter vector w and the parameter b. We derive the cost function which needs to be minimized to determine the optimal separating boundary. This cost function h takes the squared length of the parameter vector w. However, there is a constraint for each data point. The data point is denoted by a subscript I. So the constraint is yi, the data point's class, times the parameter vector w transpose times the data vector xi plus b is greater than or equal to 1. The data point's class A gives yi is equal to -1 and class B yi is equal to +1. Next, we take a look on our optimization problem from a different perspective. We will derive the so-called dual formulation. This is an equivalent formulation of the optimization problem. The idea is to shift the complexity of the constraints directly into the cost function by eliminating the parameter vector w. At first, we consider an arbitrary cost function h depending on the vector w and the parameter b. But here, we consider a constraint function g of w and b which is greater than or equal to 0 instead of 1. For this, let us take a look on two different scenarios. In both, we want to optimize a cost function h displayed by its blue contour lines. But the optimization should hold a constraint given by the inequality g is greater than or equal to 0. The contour lines of this constraint are sketched in green. The area of the constraint has a limiting contour line where g equals 0. So two situations can occur. The area of the constraint can cover the global minimum of the cost function or not. First, let us take a look on the latter scenario. In our example, the constrained optimization gives the minimum of the cost function where the outer contour line of the constraint tangents the contour line of the cost function. At this point, the cost function is minimal with respect to the constraint g. At such a contact point of two contour lines, the tangents are parallel. The gradients of the cost function and the boundary conditions are both perpendicular to the tangents. This is because the gradients are both perpendicular to the lines of constant height. So both are parallel. Note that they point along the same direction because the cost function increases from the minimum towards the lower left corner, as well as the constraint. The constraint has its smallest value 0 at the contact point and increases toward the lower left. So, the gradient of h is proportional to the gradient of the constraint function g. The factor of proportionality is lambda, the so-called Lagrangian multiplier. We define the Lagrangian function L by the cost function h minus the Lagrangian multiplier lambda times the constraint function g. If the gradient of the Lagrangian function vanishes, this gives our proportionality relation where the gradient of h is proportional to the gradient of g. Note that lambda is positive because the gradients are parallel. The second scenario that the global minimum of the cost function is within the area of the constraint g. For that case, we choose lambda is equal to 0 because we just need to minimize the cost function h. So the Lagrangian function capital L is equal to the cost function h. To find the minimum, we can set the gradient of the Lagrangian function to 0. In both scenarios, we need to optimize the Lagrangian function and hold the constraint lambda is greater than or equal to 0. This relation will allow us to shift the complexity of the constraint of our original minimization into the new Lagrangian cost function. And the constraint simplifies to lambda is greater than or equal to 0. The simplified optimization problem before minimizes an arbitrary cost function h. The constraint was g is greater than or equal to 0. We've shown that this leads to a different formulation with a so-called Lagrangian function. The constraints g are incorporated in the Lagrangian function. Now, the constraint optimization problem for the support vector machine is pretty similar to the formulation of the classical problem on the upper left. The cost function h is the function of the parameter vector w. Concrete, this is 1/2 times the squared parameter vector w. For the constraints, we can identify a function g depending on the parameters w and b of the problem. Note that yi and xi are fixed data point values. However, our constraint has the inequality with greater than or equal to 1 instead of 0. So we subtract 1 on both sides. This gives a cost function and a constraint function g which corresponds to the upper formulation. So now we can determine the corresponding Lagrangian function. Capital L is equal to the cost function part 1/2 times the squared parameter vector w minus the Lagrangian multiplier lambda times the constraint function g. Note that we have a sum over all data points here because we have a constraint for every single data point. However, our Lagrangian formulation is a mixture of the parameters w and b as well as the new Lagrangian multipliers lambda. In the following couple of minutes, we will derive expressions for the parameters w and b at the minimum. These relations will cancel the parameters w and b out of our optimization problem in the Lagrangian formulation. The expressions are obtained because the gradient of the Lagrangian function vanishes at the constrained minimum. So, at first, let's take a look on the derivatives of the Lagrangian function with respect to the w parameters. First, the term of the Lagrangian 1/2 times the parameter vector w squared gives the vector w if you calculate the derivatives with respect to all components of the vector w. This is because the vector w squared is equal to the sum of the squared components w1 squared plus w2 squared plus and so on. So the derivative with respect to a specific component, for example w1, gives 2 times w1. The factor 2 cancels with the factor 1/2. The second term in the Lagrangian is from the constraint. Multiplying the factors in the sum out, only the term lambda I times yi times the vector w transpose times the data vector xi contains w parameters. The vector product vector w transpose times the data vector xi gives w1 times x1i plus w2 times x2i plus and so on. The derivative with respect to, for example, w1 gives the corresponding x component of the ith data point. Together with the factors lambda I and yi, we have lambda I times yi times x1i. For all components, this gives lambda I times yi times the vector of xi. If we put both contributions of the derivative of the Lagrangian cost function together, we can set the full derivative to 0. Then, this can be solved with respect to the vector w. This gives the parameter vector w is equal to the sum over all data points of lambda I times yi times the data vector xi. This relates our new parameters lambda I to the old parameters w. Next, we will calculate the gradient of the Lagrangian with respect to the parameter b. The original cost function only depends on w, so here we have a contribution only from the second part of the Lagrangian, the constraints. Within this term, only a single part depends on b. This is minus the sum over I of lambda I times yi times b. So the derivative with respect to b is minus the sum over I of lambda I times yi. If we set this to 0, we have our second condition at the minimum. The sum over I of lambda I times yi is equal to 0. Next, we use these two conditions to replace the parameter vector w and b in the Lagrangian function. So, we start with our Lagrangian function depending on the parameters w and b. First, we split the contributions in the summation. Now the Lagrangian has 4 contributions. The first one is from the original cost function. The others are from the constraints. At first, consider the first 2 expressions. Both terms can be expressed by the multiplication of 2 individual parameter vectors w. For the first term, this is pretty obvious. For the second one, we can separate a single parameter vector w out, and the sum of lambda I times yi times the data point vector xi remains. This is nothing else but a parameter vector w. So in both terms we have 2 parameter vectors w, which can be expressed by the sum of lambda times y times the vector x. And with individual indices we can mix the summations. Note that the first of the 2 terms in the Lagrangian function has a factor 1/2, and the second one has a factor -1. So we can reduce both to a single term with a factor -1/2. The third contribution in the Lagrangian is 0, because we can multiply out the factor b and use our second condition on the right side. So we can put everything together. We can place the summations in front because we use different indices. Altogether, we can write the Lagrangian as -1/2 times the sum over I and j of lambda I times lambda j times yi times yj times the vector xi transpose times the vector xj plus the sum over I of lambda I. This Lagrangian cost function is much more complex than our original formulation of the cost function h with just the squared parameter vector w. But the constraints now are pretty simple. For each data point, the corresponding Lagrangian multiplier lambda I is greater than or equal to 0. Instead of optimizing a cost function with the parameter vector w squared, we can optimize the so-called dual formulation displayed here. This determines the lambda parameters. The Lagrangian multipliers are related to our parameters w via our first expression shown in the upper right. So we can determine the boundary equation with this relation. We've seen the relation to determine the parameter vector w. But what about the b parameter? Let's reconsider our classification problem with class A for y equals -1 and class B with y equals +1. Now, we focus on one class, for example class A. The margin boundary for class A is fixed in its slope because the parameter vector w is already determined. If we put the minus margin boundary across the light blue data points on the right, this corresponds to a certain value for B. You can try this for all data points of class A. And then calculate the distances of these possible minus margin boundaries to a class B data point. The closest of the possible margin boundaries is the minus margin boundary. Now we can substitute the support vector location for vector x in the equation of the minus margin boundary. Then all values are known and we can calculate the parameter b by solving this expression with respect to b. Now, you might wonder why we put so much effort into this equivalent but different formulation of our optimization problem. To understand this, we first reconsider our initial optimization problem. Typically, a cost function is minimized by an iterative optimization, such as a gradient-based minimization. In every iteration, we need to calculate the value of the cost function h with the current values of the parameters. Here, these parameters are the w and b parameters. In addition to the calculation of the cost function, we need to check our constraints. We have a constraint for every single data point. So, usually, to check all the constraints in every iteration is a lot of computational effort, especially if the constraints are difficult to calculate. Here, most of the computational effort is related to the calculation of the dot product of the vector w with the data point vectors xi. Geometrically, this expression is related to the distances of the data points to the separating boundary. It seems intuitive to calculate all these distances to determine the quality of the separating boundary. However, the calculations of the distances need to be done in every direction x of the input variables. In our example, this is just x1 and x2. So, in other words, the dot product of w times x has 2D vectors. But for higher dimensional input spaces, this leads to higher dimensional vectors and a lot of more computational effort. Now, let's take a closer look on the dual formulation of this optimization problem. The complexity of the constraints was shifted into the cost function, the Lagrangian function. Again, this new cost function is minimized iteratively. To check the constraints in every iteration, is now pretty easy because there is nothing to calculate. However, the calculation of the cost function seems much more complex. But when we take a closer look, we see that most of the computational effort is related to calculate all the dot products. But here, these dot products are between two variable vectors, a vector xi and a vector xj. These dot products are independent of the parameters lambda, so they are constant in all iterations in the optimization of the cost function. These dot products are related to the geometry of the data points to each other. This is fixed for a given data set for training, so the dot products doesn't need to be recalculated in every iteration. But how does the computational intensive dot products of our original optimization problem magically disappeared? And how can we interpret the new lambda parameters which are used instead of w and b? The intuition is to take advantage of the geometry between the data points, which stays always fixed. Let's take a look on the example on the right. The distance between vector xj and vector xi is given by the square root of the square difference vector xj minus xi. We will omit the square root here, so we have the vector xj minus the vector xi and this squared. Multiplying this out gives the squared vector xj minus 2 times the vector xj transpose times the vector xi plus the squared vector xi. When we take a look at our cost function, we find the terms of this expression in the dot products of the summations. We express our separating boundary in terms of our geometry. For example, we could choose a boundary to be located at 2/3 of our distance between xj and xi. Now, to calculate the distances is pretty easy. We just need to scale the fixed data point geometry by a factor of 2/3. This scaling is a one-dimensional multiplication between the scaling factors and the value of the terms such as vector xj transpose times vector xi. Compared to calculating the dot product in high-dimensional spaces, this is a huge benefit. This is why the dual formulation is independent of the number of dimensions of the independent variables. In the next section, we will take advantage of this dual formulation to calculate nonlinear problems with the support vector machine. Section finished. Thank you very much for listening. If you like this video, please click the like button and consider to subscribe this channel. If you have any questions or comments, please leave a comment down below. So thanks again and see you in the next section.